Welcome everyone to the statistics seminar, the last seminar for this quarter. And today is my so before I introduce the speakers, I would like to just mention that you have two ways you can ask questions. So if you have any question, you can either directly type in the chat box or Q&A section. So you can just type your question there, and Christine and I will be monitoring these two parts. So and then we'll ask the question. So, or you can actually just directly unmute yourself so that you can directly ask questions with and interact with the speaker. So it was my greatest pleasure to introduce today's speaker, Krishna. And Krishna is currently an assistant professor in the statistics department at UC Davis. And he's working on a lot of very exciting topics, including like random network model optimization and sampling and kernel methods. And today he's going to talk about a very exciting problem about the fractal Gaussian networks. So, Krishna, thanks.
Yes, thanks, Inchi, for the nice introduction. So somehow my screen got out, so give me 1 second. Let me go full screen. Okay, so I'm going to be talking about something called as Fractal Gaussian Networks. And this is going to be joint work with Subro Ghosh from NUS Singapore and Xiao Chuan Yang from Brunel University, London. And the paper is available in this archive link, and it's supposed to appear in IEEE soon, hopefully this year or next, right? All right, so I would like to start by telling about the unreasonable effectiveness, paying some homage to like Wigner's seminal article in Communications in Pure and Applied Math from the 60s. So really, if you think about it, stochastic networks, it's kind of like unreasonably effective, so to speak, in terms of like modeling interactions among large-scale data sets that are available these days. It's kind of like you would think that such simple models are sort of toy models, but actually they turn out to be pretty good in terms of like modeling some real world data as such, right? And some of such classical network models include Edwards-Renyi graphs, preferential attachment models, random geometric graphs, graphons, block models, and also in particular small world networks like Watson-Strug-Watts model and other models of like scale-free networks as well, right? And I was just talking about briefly, they have a lot of applications to like World Wide Web, collaboration networks in academia, and social and communication networks, right? So what I'm going to be talking about is, so despite this large amount of work in having stochastic network models, one aspect that has been kind of not looked into much carefully is the presence of fractal structures in random networks, right? So what do I mean by fractal structures? So fractal structures, unfortunately, in a combinatorial network, there is no accepted definition of a so-called fractal structure. So we kind of have to look for some scientific heuristics, at least in the literature, that's what is currently done. And partly this work is kind of trying to bring in a mathematically rigorous framework to model fractality in stochastic networks, right? So typically in the literature, fractality in networks is characterized by the presence of anomalous behaviors at every scale. That's the most important part. And heavy tail phenomenon for various statistic that you calculate for your networks, and kind of like power law distributions or something that arise common in these sort of fractal networks, right? And to me personally, a motivating question is like I talked with my collaborator Ethan Andres, who's a professor in our department, and he works quite a bit in astronomy. And one of the things that he would it came up in our discussion is like, is the cosmic web fractal, right? So is the universe which kind of expands, and there's like all sorts of theory from like the physics literature. So is that expansion, is this the universe fractal, right? And one of the ways of testing this is like having this CMB radiation data and looking at the spatial signatures, which kind of you can think of it as in each point in a 3D space, you have some signature, and then you want to have some tests to kind of conclude statistically that they are indeed fractal or not, and things like that, right? This is some ongoing work, and unfortunately this is not going to be the main topic of today's talk. So today I will introduce the models and the estimators and the tests, right? And in particular, these fractal structures have been known to like be believed at least to exist in all this sort of like human mobility networks and networks arising in finance and so on and so forth, right? And today, what I will do is like I will present a sparse random graph model called as Fractal Gaussian Networks that kind of it is used to understand like the fractal geometric structures that arise in networks in a rigorous and tractable manner. And our model is essentially based on something called as Gaussian Multiplicative Chaos. So it's kind of like a probabilistic concept to model the phenomenon of fractality. And I will give a brief introduction to it. And so if there's one thing that I would like you to pay attention to in this talk, and have as a takeaway from this talk, it's this parameter nu. If you think of the model that I'm going to provide as like a parametric model in a statistical sense, this is kind of like a one parameter model. So the parameter is this new parameter that I have here, which is called as the fractality parameter. So this new kind of interpolates between the purely random geometric graph or the Poisson Boolean network and like increasing networks of increasing fractality. So this new kind of, you can think of it as like a parameter which controls the fractality at the end of the day, right? So from a statistical perspective, given data, your goal is to estimate mu and so on and so forth, right? All right, so before we actually get into the model, we need to do a quick detour into Gaussian multiplicative chaos. So GMC is basically a natural family of random fractal measures. So it's basically a random measure that kind of is good from both a mathematical perspective and also like a modeling perspective, right? So it originated in the field of quantum field theory, but in the seminal works of Kahane in the 1970s and 80s. And it has been used in a lot of areas in probability and mathematical physics to study like quantum gravity, and like even something close to like statistics. It's used to characterize limits of certain random matrix models that arise in the literature. And I mean, there's also a few works in the probability group available in the larger Washington or larger Seattle area. There are several experts working on some of these sort of things as well, right? And in the applied literature, so it's used in modeling the financial assets, and also in some sense it's also well used to model problems of turbulence that arise in a lot of systems, right? As you can see, it's basically about like anomalous behavior. So turbulence is kind of a classical example of it, right? All right, so the fundamental thing that we start with is something called as a Gaussian field. So a Gaussian field, you can think of it as like a function of, so the capital X is the Gaussian field, and it's a function of little x and t. So little x is like a d-dimensional space variable, and t is like the time variable. So for each x, you can think of it as a Brownian motion, and the covariance kernel is given by this equation 1 here. So you can think of this as something like a stationary, being stationary in the space variable, right? And throughout this work, we kind of assume that, so we make few basic assumptions on the kernel. So firstly, we assume that the kernel is like normalized to be at 1 at 0, normalized to 1 at 0. And we assume that the kernel is radial, and there is some regularity conditions, which if you're curious, we could discuss, but it's kind of, you can think of it as just a regularity condition on the kernel, right? So the reason why we have this assumption is that under this assumption, as the t variable tends to infinity, one obtains what is called as the log correlated Gaussian field. And it turns out that if you have all these assumptions on the kernel function k, the corresponding Gaussian field will have this k as the covariance kernel. And the most important thing to note here in this equation is that you have a log of 1 over x minus y. So when x and y are the same, it is log of 1 over 0. So it's going to blow up, right? So there's a singularity here. So this singularity is the main thing. So in some sense, this equation is not even like a function. It has to be interpreted in a distribution sense, right? So you have to give some test functions and then like see, it's kind of like a Dirac delta function. So it has to be interpreted in a distributional sense, right? So this is the most important distinction between like other Gaussian processes or Gaussian fields that arise in classical spatial statistics even, and this model of like Gaussian multiplicative chaos or Gaussian law correlated Gaussian fields, which exhibit the singularity. So that's the main thing which leads to the fractal behavior here, right? And a classical example is something called as the Gaussian free field. So in the statistics literature, so what we call as like the Gaussian graphical model is a popular thing in statistics. So it's kind of like a special case of the Gaussian free fields, right? All right, so given such a x, so now think of x as a Gaussian field. So given such a x, we formally define this m gamma of some measure. Here I'm choosing it as a Lebesgue measure dx. So, but you can have any radon measure actually. So this m gamma is defined in this way. So where x is the centered stationary Gaussian field with that particular covariance kernel that I had in the previous slide. Right, and I would like to again emphasize that this kernel is logarithmically singular along the diagonal, right? So because of this logarithmic singularity, as I told, the Gaussian field is not interpretable as just a simple function. It only can be interpreted as a distribution. And consequently, this formula that I wrote down is not really like a formula in a regular sense. It needs to be justified, even some sort of like in order for this formula to even make sense, it kind of needs to be justified in a formal, in a rigorous way, right? So there is actually a significant technical effort to kind of make sense of this. So this, if this were true, this would correspond to like a random measure, but in order to make sense of when this is true, there is a lot of justification that goes into that part, right? And typically what happens is that you start with something that's actually well defined, which is this mt of gamma. So here, the t is appearing here. It's still not the t going to infinity case. So you have this previous Gaussian free field that we started with. And using some sort of a martingale convergence argument, we would be able to show that this particular thing, this mt of gamma, will converge to this m gamma that we started with, right? And the convergence happens in convergence could be shown in multiple ways. So there's like an L2 convergence, L1 convergence, and in this regime there is like, it's a trivial convergence. So what is the well-studied regime is basically what's called as this L2 regime. So that would be the focus of our work here, right? And coming back to what I started with, we have this fractality parameter. So the fractality parameter here is basically this gamma squared over d. So this is the thing that would control the degree of fractality, right? And as I told, we are going to be working in the subcritical regime where this gamma squared is always less than d. So we are kind of in the L2 or the subcritical regime, right? So this is the setup of what is called as this Gaussian multiplicative chaos. It is nothing but on a domain omega, which is, let's say, a subset of RD. It's just a random measure on that domain, right? But in order to properly rigorously define that, there's a lot of technical details that go into that, right? All right, so just to give some few plots, so I kind of carefully handpicked these plots to see some like weird shapes. So you see these sort of things kind of happen here, right? So the thing is, like, if you go from left to right and top to bottom, gamma increases, right? So the gamma here is the degree of fractality. So in some sense, you kind of start to see some clustered structures appearing on the domain, right? So this is more unclustered, whereas this is like exhibiting some sharp clusters in some sense, right? So the hope is that this fractal structure in the underlying domain could be leveraged to construct a network which also exhibits fractality, right? So that's the idea here, right? So maybe let me pause for a second to see if there's any questions just about this part so far.
I didn't see any questions so far.
Okay, yeah. So let's proceed then. So now let's move on to the actual from this Gaussian multiplicative chaos. How do we construct a fractal network, right? So just to recap, we are going to need a bunch of ingredients here. So there's going to be this integer d, which is the dimension of our domain. So omega is an RD, and there's this parameter gamma, which is assumed to be such that gamma squared is less than d. So and gamma squared over d is the fractality parameter, right? So it's something that we already saw. And there's this Gaussian random field that lives in D with this singular covariance kernel that I mentioned. And now you have a realization of this Gaussian multiplicative chaos random measure m gamma based on this particular random field that you chose and this parameter gamma. And there are three other parameters. So one is this little n, which is actually the real size of your network, which is like a large but finite number. And there's something called as the connectivity threshold, which is what you use to connect so-called neighboring points, right? So we will define what it is in a second. And there is an actual observed size of the network, which I denote by capital N. And this is kind of like the standard trick of Poissonization that we do in like statistics, right? So there's something, a real parameter little n, but then we kind of don't see what it is at the end of the day, but we have an actual observed parameter capital N, and this capital N is a Poisson random variable with this to be the mean, right? So little n times this measure of the whole space, right? So these are pretty much our ingredients. So given these ingredients, what we do is we sample n many points, which we call as x1 up to x capital N, from the given realization of this m gamma, which is a random measure. So now these kind of points, x1 up to xn, form the nodes of your graph, right? And what are the edges? You basically connect xi to xj, using either of these two approaches, right? A direct approach is just to connect 2 points, if only if they are within a distance sigma of each other, or you connect them with this particular probability. It's just kind of like this Gaussian kernel, and now sigma squared becomes like the bandwidth of this, right? So these are kind of standard way that people use in the literature for like constructing geometry graphs, right? So now this is kind of like just a simple picture. So if you think of your this sort of random measure over your space, if you do this procedure that I described here, this is kind of like the network that you observe at the end of the day, right? So I mean, this is just one snapshot, so it doesn't actually make any sense, but it's just for visualization purpose, right? And some of the observations that I would like to make here are the GMC measure is actually characterized by regions of certain high concentration, which are this sort of regions here, right? And obviously there are some regions of low concentration or low distribution, so there are this whole sort of thing in the middle, right? So this is how it kind of looks in this case, right? And in fact, a progressive increase in this the degree of irregularity kind of is directly proportional to this fractality parameter gamma that I'm once again referring to here, right? So as gamma becomes more, as nu becomes more and more, the degree of fractality becomes more and more for your network, right? So, and again, as I told, because of the underlying random measure being fractal, your network is also network also exhibits some of the fractality properties of the underlying measure, right? So that's basically the some of the observations that I would like to make about the fractality parameter and the FGN network. So, and a few more points is that we don't actually require the ambient space to be RD. And even if you just have a combinatorial graph, you can think of like latent space models where your latent space is RD. So if you're just given a latent, if you're just given a combinatorial graph, you think of it as like there is an underlying latent space, and then you use like any of these methods. For example, recently Node2vec is kind of popular, and there are also other latent space models. So you can use these sort of latent space models to get your ambient space RD at the end of the day, right? So this kind of makes sense even in a purely combinatorial graph that is given to us, right? All right, so let's start with so what I'll be doing next is like there's going to be some basic observations that we'll make about this network model that I discussed, and then I will talk about some theoretical results about this model, which are mostly like probabilistic in nature, and I'll highlight some of the technical issues that arise here. And I will also talk about certain empirical observations, which are very curious. And currently, it seems very challenging to show them mathematically, so justify those empirical observations that I'll talk about. And then I will look at, I'll present some statistical properties, for example, like estimating the gamma, the new parameter and testing for fractality and so on and so forth. And then I will conclude with some like real world studies, preliminary real world studies, right? All right. So let's start with a basic observation here. So I in the title of the talk, I mentioned this as like a sparse random graph model. So what is sparsity? Where is the sparsity here, right? So so I have this following proposition here. So what it tells is that if the FGN has the size parameter little n, then for any value of gamma, if I set my sigma parameter, so recall that the sigma parameter is like the connectivity threshold parameter. So if I set it in this particular way, it turns out that the expected number of neighbors of a given point is basically asymptotically of this order, constant order, right? So some number between 0 and infinity, right? So which in particular doesn't depend on n at all or little n at all, right? So what this means is that intuitively, although although there's like a large number of nodes in a real world network, if you're at a local node and look around yourself in a local neighborhood, it's only like O of 1, which is like a constant order of connections, right? So this is basically the sparsity part of our network model, right? So this turns out to be very useful for modeling sparse network, which almost all real world networks are, right? So most of the real world networks are very sparse, right? So this is an important observation, which is also kind of like helpful from a practical modeling perspective, right? And the next thing is that, so recall that we are doing a Poissonization. So the little n is basically the size of your actual network, but the capital N is what we start with. So the network size is and conditioned on the random measure. Basically, this network size parameter capital N is a Poisson random variable, as I told, with this mean. And if you think of, so if we recall some basic facts, that if yi is a sequence of Poisson random variables IID with this mean, then n is, so the capital N is basically the sum of these things in distribution, right? So it's a basic fact. So given this, if you take the ratio of capital N over little n, this will eventually converge to this m gamma of the overall space omega as n little n goes to infinity. So the bottom line here is that the little n over, or capital N over little n, is also of 1 with high probability when n goes to infinity, right? So in some sense, it turns out that this Poissonization trick is kind of also helping us to infer the actual size of your network, right? So we can make this argument a little bit more rigorous and tell that the probability of capital N over little n exceeding 2 times this m gamma of omega is basically some constant little c times n to the minus p. So this is kind of like a polynomial, or like this concentration is like, so this will be true for any p greater than 0, which means that it's like a polynomial. It's a faster than polynomial rate, but not a pure exponential rate, or faster than any polynomial rate, but not a pure exponential concentration. And obtaining a pure exponential concentration result here is an open problem, right? And it involves actually making progress in understanding the GMC measure itself, right? So this is one thing I would like to point out. And now let's move on to do some sort of empirical observations, right? So we want to like empirically check indeed the network is like highly clustered with like a lot of like high density regions and then like extremely low density regions around it. So we have the famous clustering coefficient. So for a given graph with nodes being v1 up to vn and this h set, ni is basically the neighborhood of a node, particular node vi. So then we have what is called as the local clustering coefficient and the average clustering coefficient, which kind of is a standard measure of like how it's like a scientific measure of how clustered a network is, proposed by Watts and Strogaard. So if we plot for a realization of Gaussian multiplicative chaos, if we plot the clustering coefficient versus this new parameter, you see that as nu increases, the clustering coefficient also increases, which means that as the degree of fractality increases, the clustering effect in the network is also prominent, right? So empirically, this kind of at least in a heuristic level, in terms of like widely acceptable notions of clusterability of a network, indeed, that seems to be captured in our model, right? And we also plotted the degree distribution. So, and you see that when, so in this figure, if you go from the left to right, the parameter nu kind of goes from 0 to a larger number. So you see that, and I've removed all the nodes that have no neighbors. So which is a really large number in our like fractal networks. So if you ignore that, you see that when nu is 0, you have this Poisson network or a Poisson kind of a distribution. And then when as nu increases, you kind of tend to the power law, which is also confirming what I told in the initial part of this lecture. Like the parameter nu is kind of like the parameter controlling the degree of fractality that is available in your network, right? All right, so now let us move on to some theoretical properties that you would like to discuss about our network model. So like the most basic things that you can start counting in a network, in a given combinatorial network, is you start with like the edges, the triangles, and so on and so forth, right? So you start with some basic statistic that you care about in your network, right? So it turns out that you can have, in fact, a formula. You can kind of compute a lot of subgraph statistic or motif statistics analytically for this FGN network. However, so far our computation is only in an asymptotic sense, in the sense that n is going to infinity, and it's also only in expectation, right? So what I have here is, if you have a network with original size parameter little n, and rho is, recall, if you recall, rho is basically the uh, the order of your local neighborhood, which is a constant, right? So the expected count and the expected triangle E and T respectively satisfy this formula. So for any nu which is actually less than 1 for the case of edges, you have something like this. So the most important thing that you would want to focus on in this page is this n to the 1 plus nu, right? So this is basically appearing in both the edge count and the triangle count, right? So in terms of n, this is the order of your expected number of edges and expected number of nodes, right? So you have to compare this, for example, with in the case of edges. If it's a fully connected graph, you will know what's the number of edges, and if it is a fully connected graph, or if it's an Ed-Dorsey graph, you can compare, calculate this expected edges and so on and so forth, right? And it's not only this, so you can also do other motives in some sense. So for example, if you have a k-spoke with a hub V, so this is another motive where you kind of have a central node V, and then you have like nodes U1 up to UK that are all kind of connected to the C. So it's kind of like a cycle, it's a bicycle or a bike, like a hub and spoke sort of thing that appears in the wheels, right? So if you have that motive, and K is like a parameter for this, right? So of course, a one spoke is also the edge, and it's a two spoke is also known as a cherry in the literature. So for this motive, if nu is satisfying this formula, the expected number of this motive, right? So the expected number of SK, where SK is the hub spoke model or hub spoke motive with K spokes, that is also of the order of n to the 1 plus nu, right? And you can also do more generally for k-cliques. So if you have a k-clique, a k-clique is nothing but a complete subgraph with k vertices. So if you denote qk to be the k-clique, the number of k-cliques in a realization, the expected number of qk is again of the order of n to the 1 plus nu, right? So the expected behavior of all this sort of like motives are of the order of n to the 1 plus nu for the given graph, for the given FGN model, right? And in fact, we believe that for all subgraph counts, the order of the expected order is essentially is n to the 1 plus nu. We have empirically verified these things as well, but mathematical proof is kind of like, again, a little bit more challenging due to the technicalities involved with dealing with the GMC random measure, right? All right, and another thing that I would like to point out is, or probably it will be there in the end, so maybe I will get to it in the end, right? So now, yet another curious observation about the spectral properties of this fractal Gaussian network. So, I mean, we all can kind of agree that looking at the spectrum of the Laplacian matrix is extremely useful, and it has a lot of applications like clustering, even like regression, classification, all sorts of like modeling problems in statistics. Laplacian matrix plays a central role. So what happens if you look at the Laplacian matrix of FGN model, right? So just to fix things here, I'm going to use the Laplacian, which is just D minus A, the diagonal minus the adjacency on n vertices. So this is basically the eigenvalues of this matrix L, right? So what's happening here is that in the left-hand side, I have the full histogram of all the eigenvalues, and on the right-hand side is only the zoomed in part of this bulk, what I call as the bulk, right? So as you see here, the eigen spectrum is essentially seems to be composed of two parts. One is like a continuous bulk, which is kind of like this semicircular or kind of semicircular law that we are all aware of in the context of, like, say, at least dense Erdős-Rényi models. But on top of this bulk distribution, there is also like these peaks, right? So these peaks kind of correspond to the fractal behavior that appears in your network. Essentially, it turns out that it's a non-trivial statement, but it turns out that these peaks correspond to the fractal properties, right? And the sparsity properties that is available in the network. So, and this is kind of true for various values of nu that is non-zero, right? So it's like increasing nu, and you see that there is always like a bulk, but then there's also like a lot of peaks interspersed on the spectrum, right? So this is, I'm just going over this 3 plots that I have here again, right? So basically, as I told, there's like a singular component, which is basically eigenvalues with extremely large multiplicity, which is kind of scattered all through the spectrum, and of course there's a bulk, right? And the bulk is basically, it seems to be an absolutely continuous component, right? So such a kind of nuanced or a multi-scale structure, as in my understanding, and after talking to a lot of experts as well, this multi-scale behavior in the empirical distribution of the eigenvalues of this Laplacian matrix seems completely novel in some sense. So any of the other random matrix, most of the other random matrix models that people have looked at, this sort of a behavior apparently doesn't seem to be there, right? So proving anything about this theoretically seems to be a challenging open problem. So I'd like to mention here that even for sparse Erdős-Rényi graph, there's a lot of open questions about understanding the eigenspectrum. So here it seems to be like a little bit more challenging than that, right? All right, so now moving on to the statistical aspects of this model. As I told, we only have one parameter, nu, for our model. So if you want to estimate that, we kind of use the expectation calculations that we did. So roughly speaking, the expected value of the edges is of the order n to the 1 plus nu, right? So this n to the 1 plus nu, you can kind of invert it, take log on both sides, and then like bring the negative 1 to the left hand side, and you can kind of get, excuse me, something like this as your estimator for your nu. So we call that estimator as nu hat. And a proper justification is something like, you can write the log e as something like this, and we know that e over n to the 1 plus nu is omega of one quantity, essentially, which means that the log e over log n is like almost 1 plus nu when n goes to infinity. So we also know that log n is of the order of log little n, which plus this 1 plus o of n, little o of 1. And if you combine these two facts, you will eventually see that log e over log n minus 1 is approximately nu. So here it's basically the empirical version of that, right? So that's what we have it as our estimator for the fractality parameter. And of course, there is no need to use E specifically, the number of edges. We calculated that, we previously saw that all the small order motif are all of the order of like n to the 1 plus nu in expectation. So you could kind of play this game with those sort of motifs as well, right? And the next question that we want to address here is that what do you do if you given a network or a snapshot of a network, how do we conclude that this that given network is a fractal network or exhibits fractality or not, right? So we kind of, as I told in the beginning, there is no agreed or like a classical notion of fractality of a network. So we are kind of putting forward our model, and based on our model, we are proposing this new parameter as a parameter that you could kind of test for to declare presence or absence of fractality. And I hope I have convinced that this new parameter is actually exhibiting or like capturing certain fractal behavior through my previous experimental validations that I kind of showed you. So what we can do is like under my null hypothesis that the network is not fractal, I kind of test for whether nu is equal to 0. And under my alternate hypothesis, I have that nu is greater than some nu naught, which is like the minimax, the radius at the end of the day, right? So the problem, hypothesis testing problem now is like basically you want to test whether nu is equal to 0 or nu is basically greater than some number nu naught, right? And by basic under the null, it's basically the Poisson random graph model, the standard random graph model, right? So under H naught, essentially using a basic CLT argument, one can conclude that the E is where E is basically the number of edges, that should be of the order of n plus 1 plus mu naught over 2. And on the other hand, with under our H1 model, we can kind of conclude with large probability that E should be of the order of n to the 1 plus mu naught over 2, right? So this suggests that you can reject H naught if the value E divided by capital N, which is what we actually observe, to the 1 plus mu naught over 2 is large, right? So this is kind of our test. So at this level, what I have told here is a heuristic argument. So one of the problems is like, for example, what's the minimax rates and things like that. It's highly unclear. So I believe there's a long way to go to characterize minimaxity and things like that in this case, right? So and basically this is the thing that I'd kind of be using to test the fractality for the astronomical problem that I was talking about in the beginning of the talk. And we have to talk to the domain experts and kind of see whether this makes sense to them or not, right? So that's ongoing work. All right, so now let me conclude my talk with the preliminary network data analysis, real world network data analysis. So I'm kind of I'm hoping that if you are a mathematician or a probabilist, it's already interesting to figure out a lot of these open problems. But if you're a practitioner, I would like to at least try to convince you that it's not just a pure mathematical toy to play with. It's actually something meaningful in the practical context as well. So what I've done here is there are two standard network data sets called as the answers and the Flickr data set from the Stanford network dataset collection. And the answers dataset is like from the Yahoo Answers portal and depicts the interaction of the users there. And Flickr is the same for the photo sharing website Flickr. And these are the order of the nodes and edges in the answer dataset, and these are the orders in the Flickr dataset. So as you can see, they are extremely sparse networks, and people, especially who worked with these data sets, always, if you look at the published papers, some people kind of heuristically claim this is like a power law behavior, and this in fact some people explicitly claim in their published works that there is reasons to believe fractality exists in this network and things like that, right? So that was the motivation for using these data sets. So now, as I told, using the previous methodology that I described, I am using the previous methodology to estimate the parameter nu. And what I'm doing is like I'm generating an FGN graph from this estimated value of nu. and I already have this actual data from this answers in the Flickr data set. So I'm going to compare, like empirically compare the behavior of these two, like simulated network and the actual network, right? So where the simulated network's parameters are kind of estimated from the network. And of course, there's a data reuse issue here, because like I'm using the same parameter to test and estimate or like do the post-processing and estimation in some sense. But I mean, what I did was like, I mean, doing cross-validation or any sort of data splitting in network itself is like a big unresolved issue, but I use some of the techniques that people are using in practice for this data splitting on networks. And I at least made sure the testing part and the visualization part are independent. So now what I'm specifically plotting is that the degree distribution of both the networks and the scree plot. And just to recall, the scree plot is nothing but the eigenvalues of the adjacency matrix versus their rank, right? And here is the results for both the degree distribution and the on the answers dataset, and the FGN with the estimated parameter, and Flickr and the FGN with the corresponding estimated parameter. And it seems to kind of overlap, and these are averages. And it seems to at least visually make it's not at least a good. It looks like at least a good first order approximation to this networks, right? And the same happens for the scree plot as well. For I think the x-axis has to be, I mean, the y-axis has to be the scree plot here, right? Okay. So just to conclude my talk here, so what I introduced was a fractal Gaussian network, which is a framework for modeling sparse networks with fractal behavior. And as I was kind of alluding throughout the talk, so there are several open problems, which is one of the reasons why I kind of present this work rather than some work that I already completed and well understood. So some concrete problems here are, so concentration requires novel techniques. So you give me any of the techniques, Herbst argument and functional inequality, you take any of the existing proof technique, it doesn't seem to work. Second moment method doesn't work. So it seems like fundamental advancements needs to be made to get any concentration results here. And the spectral behavior again is extremely interesting. So if you're aware of random matrix spaces, which there are a lot of people in the probability community in Seattle who are working on that. So there is so you can kind of interpret the underlying geometry of the space through this discretization of the Laplacian that we are looking at, right? So you will eventually have, so in practice, I mean, what's widely used in statistics now is basically you have a Laplacian operator, but with a fixed density. Here, it's a Laplacian operator with a random measure or a random density. And understanding that behavior is and this discretization is like very interesting. And and because I sit in a stat department and also this is a stat talk, minimax rates for estimating fractality and testing is open. And of course, I hope this model is also widely used in other applications as well, right? All right, so with this, I will conclude my talk and I'll be happy to take any questions.
Great. Thanks, Krishna.
Thanks.
Any questions for Krishna? So actually, personally, it's very exciting talk. I actually have a couple of questions. So,
sure, yeah.
Others might be composing the questions, so I may ask. So, my first question is that you I think this idea about estimating new hat using log edge count divided by log node count, like it's kind of very clever. So I'm just curious, do you have like convergence rate or asymptotic distribution about this quantity?
Okay, so I have a convergence rate. I have a concentration result, but not the asymptotic distribution. So it's in the paper we have a concentration rate, but the concentration rate is not good. And it's kind of related to this problem that I told. So if you can get a pure exponential concentration for estimating the capital N over, I mean, basically estimating the little n, I can get a much faster rate for everything else. But this is the bottleneck there to get a concentration. And asymptotic distribution seems out of my hand now. Yeah.
Right. So actually, I'm curious that because we know that like as you also mentioned that the age count is not the only ones, right? So other motives, like a number of clicks can also be used. So exactly, I wonder that in reality, let's suppose you compute the estimator based on a couple of different motives. So they may give you different, slightly different value of new heads. So how do we handle that?
No, yeah. So, okay. So that's a very good point. So I actually tried for the same like instance of the GMC, you could use like multiple different motives and get various values. So in terms of like these plots actually that I had finally, in a way, it's not really too different, the GMC that I get from this estimated values. But a proper aggregation and then like having a consistency at least sort of result, that is possible. Like the consistency result should be possible. But again, concentration, I don't know whether it would help in obtaining a concentration, which I don't think it would. But yeah, so this aggregation is like extremely interesting. Yeah, that's a very good question. Yeah.
Okay, thanks. So actually, I'm also thinking about that. Would there be something kind of like a because when you use different motifs, some of them are based on two ages, some are based on triangles, and you can have like k-clicks, right? So I wonder, would there be actually some benefits, something like a bias variant trade-off type of things when you're trying to use a more complex? Because if you use a more complex motif, the number of counts is going to be smaller.
Maybe
you're going to get more reliable things. So I'm just curious.
Yeah, no, that's again a very good point. So all these results here are only expectation results, right? So getting a concentration result here would really answer all of the questions that you're asking, like which would have the least variance, and then like you probably use of course if you go down the list in terms of like motive, like the more complex the motive is, probably the guess is like the variance is going to be large as well, and you'll probably have a sweet spot. Yeah, but so right now it's only the expectation results that we have, as I pointed out. And yeah, so getting the concentration or even, I mean, variance, I believe is we can do it. But yeah, so I think even just calculating the variance and looking at which motive to use is but it's doable. Yeah.
Right. And actually, my final question is also related to this slide.
I see.
So the concept of CT gamma D versus CE gamma D, I think in the triangle cases that we saw something like 1 minus U, right? There's a 1 over U, like the constant, right? So in the integral, you have the 1 over U minus V, like to the power of gamma squared. I think that's because if you you fix one, is it because like you fix 1 point, so you are thinking about the other 2 points, the chances that they are occurring in a small neighborhood?
Yeah. That's correct.
I see. So that's how you that's how you actually get this result.
Yeah. It's based on that argument, and then like so dealing with the GMC part is the main challenge, but the argument is exactly flowing like that. Yeah.
I see. Okay, very cool. Great. Okay, questions from the other audience? Yeah, I think it's the last day of instructions.
Yeah. I can imagine.
We're looking forward to the end of the course.
There seems to be something in Q&A.
Oh yeah, there's a question in the Q&A. Yes, so this from
this is a very good question. Yeah. So that's perhaps the question is perhaps methods similar to those used in Schramm lunar evolution can be used to study the scaling limits of this graph. Exactly. So that's the this part here. So any of this random metric spaces and SLE, basically SLE is like Schramm-Lohr evolution. Yes, that's a very good point. Yes, yeah. And that would also exhibit the that would also demonstrate or like give a justification for this sort of fractal or like multi-scale behavior of the Laplacian spectrum.
Great. Other questions? Okay, so if no other question, then let's thanks Krishna again for this really exciting talk. Very, very cool results. And thanks everyone for participating.
Thanks.
And hopefully we'll meet sometimes in the future in person.
Yes, I hope I was there in person. But unfortunately not. And I see Alex, and I just want to say hi to him. Yeah. Bye.
Okay, great. Okay, see you.
All right. Yeah. Have a good day. Bye.
Bye.